In our last class, we tried to look at the definition of mappings and function, and we tried to compare the two concepts to see their relationship and the contrast between the two functions. And our conclusion was that all mappings are functions, but not all functions are necessarily mappings. So today we are going to proceed with the topic, and we shall be looking at the definitions of some terms that are associated with mappings and function. So there are some certain terminologies that we need to master as so that we can be able to gain some benefits as we continue with this concept. So I will go into the definition of those terms, but before then I will make reference to two different sets, so that we use the two sets to form a mapping, and with reference to that mapping we'll be able to explain the terms. So let's see. Consider two non-empty sets P and Q as follows. You know that we define mapping to be the association between two non-empty sets. So it follows that for us to look at some terms that are related with either mapping or function, so we have to consider two non-empty sets. So here I have decided to make reference to two non-empty sets P and Q. So we have set P equals x such that 4 is less than or equals to x, less than or equals to 25, and x is a member of a perfect squares. So this is your set notation. So, and with this set notation builder now, we can get the elements of P. So what are the elements of P? So it implies P is equals to 4, 9, 16, and 25. So these are the elements of P. Why? Because from this notation builder, we have been told that the elements of P refers to x such that 4 is less than or equals to x. So because of this equality sign, we say 4 equals to x or x equals to 4. So 4 is the first element. Then 4 is less than x. So what are the values of x that will be such that 4 will be less than what? Less than x. But if we have to get this value, we are going to have 5, 6, 7. But there is another condition there here, that x has to be what? A perfect square. So from all the values of x which 4 is less than, we only pick out the what? The perfect squares. So that's why we ignore 5, 6, 7, despite the fact that they satisfy the condition 4 less than x, but 5 is not a perfect square, 6 is not. So the perfect squares there are 9, and I believe we know what perfect squares are. So we have 9, 16, and 25. So we have to stop at 25 because we are having it here as x is less than or equal to 25. So because of this equality sign, so we have to include what? 25. So now let's look at set Q. Set Q is given as a such that a equals square root of x, and 4 is less than or equals to x, less than or equals to 36, and x is also a member of perfect squares. If you look at this now, the elements of Q are a, and a has been defined as the square root of x, and x is further defined as 4 less than or equals to x, less than or equals to 36. If you look at this notation builder very well for x, it's just the same thing as what we have for what? For P, except that in the case of P we stopped at 25, but here we are going to stop at 36, and those values we take their square roots for us to get the element of Q. So if that is the case, we just pick each of these elements and take their what? Their square roots. But don't forget that a square root is always associated with a plus or minus. So in that case, we are going to have Q equals plus 2, minus 2, plus 3, minus 3, plus 4, minus 4, plus 5, and minus 5. Then we have plus 6 and minus 6. So we would have stopped at plus 5 and minus 5. Again, being the range given here is also x less than or equals to 25, like we have here. But here what we are having is x less than or equals to 36. So if x is less than or equals to 36, then 36 will be part of the value of x, and square root of 36 will either be plus 6 or minus 6. So if you take the square root of each of the elements here, square root of 4, you can have either a plus 2 or a minus 2. That will make the element of what? Of Q. So clearly now you can see that there's interrelationship between set P and set Q, which simply means for this every element in set P, if you take its square root, you arrive at the corresponding element in what? In set Q. So that means there's an association between P and Q, so they can exist as a what? As a mapping. So if that is the case, we can express the mapping, that is the association between P and Q, as P maps Q according to a particular rule. The rule here is the square root function. So we say P maps Q according to rule F. So the rule F here is the square root of each of the elements of P. So we can write it using this notation, or another way of writing it is we may say F such that P maps Q. So that is, F is a rule in this case, which is a square root, such that every element of P maps what? Q. So in either case, we have our notation for the association between set P and set Q, and we simply call this association a what? A mapping. But if you look at it very well, this mapping as it is now, we can now represent it with arrow diagram. Now if you look at this set P and set Q, you will see that it is just the same as the set I gave you in the last checkpoint exercise. So except for the fact that set Q has up to the range of 36 instead of 25. So which simply means I'm using a stone to kill two birds here. So by the time I draw the arrow diagram for this very set P and set Q, it will serve as a kind of correction to the exercise I gave you in our last class. So let's move on. Let's look at the arrow diagram. So the arrow diagram for this mapping, we have learned this before, that we can represent a given mapping with arrow diagram. So let's have the arrow diagram for this mapping, that is the arrow diagram for the association between set P and what? And set Q. So let's see. So we have set P. So what are the elements of set P? So we have 4, 9, 16, and 25. I told you that you can arrange it anyhow inside this oval, as long as all the elements that are enclosed herein are actually elements of set P. You don't have any problem. So another person may arrange his own as 9, 4, 16, 25. Another person may choose to arrange as 25, 9, 4, 16. Anyhow, so just take note that all the elements that are enclosed here are belonging to what? To P. So we do the same thing for Q. So we have Q whose elements are plus 2, minus 3, minus 4, minus 2, minus 6, plus 4, minus 5, plus 3, plus 6, and plus 5. So you can see now that I have decided to arrange in different order from how it is listed here. So we have plus 2, minus 2. So I have my plus 2 followed by minus 3. But you see that every element here are actually belonging to set Q. So your order does not mean anything. Now, what's the rule that connects them? So we have rule F. So the rule F here is the square root of each member of P to produce Q. So with this arrowhead now, look at the direction of this arrowhead. It simply means I'm setting my P as the input and my Q as the what? As the output. So based on this rule, and I said this rule implies square root as it is very clear in the set notation builder given. So it simply means for every element of P, which are the inputs, when you take their square root based on this rule F, you arrive at a corresponding element in what? In Q. So we say P maps Q according to this arrow diagram. So let's use arrow connector to show the relationship between each of the elements of the input and the output. So we have 4. So when you take the square root of 4, you can have a result of plus 2. So we can say 4 maps plus 2. But as well, when you take the square root of 4, you can also have what? Minus 2. And that's why we are having 4 maps minus 2. So with this first result now, we can clearly see that this our illustration is actually a mapping but not a function. You can still remember what we discussed in our last class. Why is it not a function? It is not a function because 4 as an input is having 2 different outputs, and with that it disqualifies this association or this relationship to be labeled as what? As function, even though it is a what? A mapping. Because when we call something a function, based on what we discussed in the last class, we said a function must be such that each input must have one and only one output. But here 4 is having 2 different outputs, so it can never be a function. But this relationship can still be a what? A mapping. That's just a revision of what we have learned. So let's move on. So 9 maps minus 3. You can see 9 maps minus 3 because the square root of 9 can give us minus 3, and the square root of 9 can also give plus 3. So 9 will also map 3. So we do that for the other elements. So we have 16 maps minus 4 as well. It also maps plus 4. Then we have 25 maps minus 5, and as well that 25 also maps what? Plus 5. So like I said, this is the arrow diagram, and this arrow diagram clearly shows that this relationship between P and Q, even though it is a mapping, it is never a what? A function. Now, with this result now, we can now learn our terms, which is the major thing, the major aim of this presentation of this class. So the terms, what are the terms that are associated with either mapping or function? So since I said this is a kind of a mapping but not a function, all the terms we are going to be discussing, you can use this term in relation to either a mapping or a function. So regardless of whether relationship is a mapping or function, all these terminologies still apply. So let's look at the terms one after the other. So the very first one I'm going to look at is what we call domain. So domain is a set of input elements of a given mapping. In other words, what can go into a given function is called the domain. Each element of the domain is sometimes called the pre-image. So this is the definition of a domain. It's a set of input elements. So all your input elements in a given association or in a given mapping, all the input elements, they are collectively referred to as what? As domain. Whether that association is a mapping or function, you can see even in this definition I have used the two terms interchangeably. Here I said mapping and here I said what? Function. So you can use domain. You can use all the terms that we shall discuss. You can use it interchangeably to refer to either mapping or function. So the domain of a mapping or the domain of a function, they are the set of the elements that act as what? As inputs. That is, the elements of the set that act as what? As inputs. So in this notation of mapping now, all our P, set P, is known as the what? As the domain. So all elements of set P, when we gather them together, so the collection is also called the what? The domain. So each element of the domain, each element of this domain now, that is 4, 9, 16, 25, each of these elements, we call them what? Pre-image. So that's another word, we say pre-image. So please take note of that. So each element of your domain is also known as what? Pre-image. So take note of that. So if that is the case, we can now list out the domain in our mapping here. In this illustration now, what will be our domain? Our domain refers to what? To set P. So therefore we say domain for this consideration, domain will be equals to set P, which has elements of 4, 9, 16, and 25. So these are our domain. All your possible inputs, all elements that forms your input automatically belongs to your what? To your domain. So please take note of that. I believe with that we understand the terminology domain as it is used in mapping. So the next one is what we call codomain. So codomain is a set of all possible output elements in a given mapping. In other words, what may possibly come out of a function is called the codomain. So what do we mean by this? Now, your output set, all possible output elements in that set is referred to as your what? As your codomain. So please take note of that. We said what? All possible output elements, all possible. So which simply means the entirety of all the elements of your output set. We call it what? The codomain. So here now that we have just said P is our domain based on the first terminology explained earlier. Then your Q now, all the element that belongs to what? To Q. Anything that falls into Q as elements of your output, we automatically call it what? Codomain. So that is why we said what may possibly come out of a function is called the what? The codomain. So what we mean by possibly coming out here is that anything that belongs to Q is a codomain, but each element of the not all elements of the codomain must actually have an association with the element of the domain. For example, look at this -6. This -6 is not connected to any element here, but it still belongs to what? To Q. So it's a member of the what? Of the codomain, even though it does not associate with any element in the domain. So all your possible output elements, all once it is in the output, then it is regarded as what? As a codomain. So in this case now, if I have to list out the codomain, we are going to have codomain equals set Q given by +2, -2, +3, -3, +4, -4, +5, -5, +6, and -6. So these are the elements of the codomain. All elements of output set in a given mapping, we refer to it as what? As codomain. Then from there, we also discuss what we call range. This is another term. Range is a set of all actual outputs in a given mapping. That is, what actually comes out of a function is called the range. Each element of the range of a given mapping is sometimes called the image. Now look at this now. Your range now is the set of all actual outputs. Actual, look at that. All actual outputs. All actual outputs. All actual outputs. Let me just highlight that for the sake of emphasis. So all actual outputs, unlike what we said about codomain, all possible outputs, which simply means in the case of range, any element that will belong to your range must be an element that is connected to at least one element in your input set. What does that mean? In this case now, if you want to list out your range, minus 6 and plus 6 will not be part of your range even though they are part of the codomain. Why are they not part of the range? Because minus 6 and plus 6 do not have any image or do not have any element, they do not have any association with any element in our input or domain. So in that case now, that's why we said each element of the range of a mapping is sometimes called the what? The image. So these two now is an image. Image of what? Image of 4. 4 is the pre-image, 2 is the what? Is the image. Or we say plus 2 here is a member of the range. Then minus 3 is also a what? A member of what? Of the range. Unlike plus 6. Plus 6 can never be a member of the range because it is not associated with any of the input elements. The same thing applies to what? To minus 6. So that simply means if we are to list out our range now, we are going to have range equals plus 2, minus 2, plus 3, minus 3, plus 4, minus 4, plus 5, minus 5, and that's all. You can see now that we did not include pluses and minuses. Why? Because pluses and minuses, while they are part of the output element, but they do not have any association with any input element. Hence, they cannot be part of our what? Of our range. And that's what we mean by range is a set of all actual outputs. That is, all elements of the domain that is of the codomain rather that is connected to at least one element in the domain makes up our range. So, and that is that about that. So these are the terms that are associated with either mapping or what, or function. So in our next class we shall look at the different types of mappings or different types of functions that we have. So if you have any question, you can always contact me. Thank you.